Hello, my name is Anna Rensch. I am a PhD candidate at the University of Guelph. Today, I will be talking about how complex rearing aviary design promotes load-bearing activities in laying hen pullets. Laying hen housing is undergoing a major shift by turning away from barren, conventional cages towards more complex alternative housing systems like furnished cages or the aviary depicted here on the slide. While the EU has already made that change, Canada is prepared to alter all laying hen housing to alternative systems by 2036. Aviaries are multi-tier systems with resources being distributed throughout the vertical space. Their benefit is that they offer space to perform a large range of behaviors such as perching and dust bathing. On the other hand, the high complexity can lead to emaciated birds that were unable to locate food or water, or injuries such as bone fractures and deformities. The latter is a major welfare concern in laying hens, specifically affecting the keel bone. The keel bone is the chicken's sternum, where the pectoralis muscles are attached to. This means the keel bone is involved in any behavior that uses the wings, as well as general breathing. Therefore, it is not surprising that keelbone fractures are considered to be painful and can even impair a hen's mobility. Here you can see two x-rays of a keelbone, with the one on the left being what it's supposed to look like, and the one on the right showing fractures and deformities. Keelbone fractures may be a consequence of low bone mass or osteoporosis, which in turn has been associated with a mix of genetic, housing, and nutritional factors. Housing can counteract osteoporosis by promoting dynamic bone load exercise, which is behavior that puts mechanical strain on the bone and facilitates bone formation, strengthening that bone. Such load-bearing behavior is most effective during skeletal development. Research has shown that the hens reared in aviaries have indeed larger keel bones compared to cage-reared hens, and even showed reduced bone fracture prevalences at end of lay, meaning that housing design during pullet development could be used to grow pullets with less osteoporosis and lower chance of keelbone damage. However, these studies did not look at how different genetic strains were affected, nor did they assess the specific load-bearing behavior performed in the different pullet housing systems. Chicks are moved into their pullet housing right after hatch, where they will stay for approximately 17 weeks before being transferred to their adult housing. In pullet aviaries, chicks are confined within brooding compartments during the first few weeks for manageability and their own safety. When the brooding phase ends, the systems are opened up, giving pullets free run of a litter area and multiple tiers. The design of pullet aviaries is very variable, with little to no guidelines. Generally speaking, rearing aviary designs can be grouped into three distinct styles. In the three different styles, the brooding compartment especially differs significantly in their space and complexity. We were asking how rearing aviary design and pullet genetic strain affects the pullet's development. We hypothesized that aviary complexity would influence how much load-bearing behavior is performed, which in turn would influence bone strength and fracture susceptibility. We predicted that increased complexity increases the amount of dynamic load-bearing behavior, which includes all forms of locomotion. We are also interested in load-bearing involving the wings specifically, those engendering mechanical strain on the keel bone, where wing muscles are attached. This would include wing flapping, flying, sparring, and wing assisted running, which we predicted would increase with increasing aviary complexity. To answer our question, we raised 3 flocks of laying hen pullets in each of the 3 distinct styles of commercial pullet aviaries. We raised 2 commercial strains of laying hen pullets, the white-feathered Lohmann-selected Leghorn Light and the brown-feathered Lohmann Brown Light. Here you can see a side view of an aviary, a picture of the brooding compartments after chicks are placed, and a photo of the free run phase. Aviary style 1 offers the least spatial complexity, while during the brooding phase, chicks are confined within a cage with 2 perches. Once open, the free-run phase offers access to a litter area and 3 system tiers. Aviary 2 offers a bit more complexity, with an elevated platform and 3 perches in the brooding compartments. The free-run phase offers a litter area and 2 system tiers. Aviary 3 has an open concept brooding compartment, where chicks can access the whole length of the barn, a swinging platform and 6 perches. Again, the free-run phase adds a litter area and multiple tiers. This aviary is the most spacious and complex of the 3. Bird density was kept consistent between all 3 aviaries in terms of litter and floor space per bird. To assess load-bearing behavior performed in the different aviaries, we did live observations at 3 time points during the brooding phase and free-run phase. Behavior observations were done using the Pocket Observer app by Noldus. 2 observers were present during each observation period. At each time point, focal birds were selected by proximity to predetermined locations within the systems. Each focal bird was then observed for 5 minutes and all behavior coded continuously. The number of focal birds per aviary was set at 10% of the population size during the brooding phase and 5% during the free-run phase. Half that in the 1st and 7th week due to logistics. Behavior observations were pooled into 2 groups. Dynamic load-bearing, which includes all locomotion, listed here. So walking, running, sparring, and all vertical transitioning. Wing-involved load-bearing is all behavior that would strain the keelbone, so everything that uses the wings such as wing flapping and all wing-assisted locomotion. We collected data on 3 flocks with 3 time points per phase, which gave us 2,013 observations in total for the brooding phase and 836 observations for the free-run phase. Statistical analysis was done in R using generalized linear mix effect models, using aviary design, strain, and their interaction as fixed effects, and time of day, nested in age, nested in flock, as well as aviary section nested in aviary design as random effects. Any post-hoc analysis was done using the Tukey test with Bonferroni corrections for multiple testing. As we analyzed both dynamic load-bearing as well as the more specific wing-involved load-bearing for both phases, this gave us 4 fitted models in total. As data on wing-involved load-bearing was heavily zero-inflated, they were analyzed as binomial. The results for dynamic load-bearing during the brooding phase is on the graph on the left-hand side and that for the free-run phase on the right-hand side. On the x-axis of these graphs, you can see the rearing aviary styles with 1 being the least and 3 being the most complex. On the y-axis, we have the predicted frequency of dynamic load-bearing behavior in rates per minute, displaying the model fit, standard error, and confidence interval. Dynamic load-bearing is affected by style and strain throughout rearing. In the brooding phase, chicks in aviary 3 performed more dynamic load-bearing than those in 2 and 1, and whites more than browns. In the free-run phase, there is an interaction of aviary design and strain, with white chicks in aviary 2 and 3 showing more dynamic load-bearing than any other group. The x-axis here shows again the aviary style, while the y-axis shows predicted odds of wing-involved load-bearing, as well as the standard error and confidence intervals. Wing-involved load-bearing is affected by aviary style, though by a lesser extent than the dynamic load-bearing, as you can see by these massive confidence intervals. In the brooding phase, there is a trend for chicks in aviary 2 and 3 having higher odds of wing-involved load-bearing, while there is no effect of strain. In the free-run phase, there is a trend for pullets in aviary 2 having higher odds of wing-involved load-bearing than pullets in aviary 1. There is no effect of strain. Coming back to our predictions. we hypothesized that higher complexity would lead to increased dynamic load bearing, which was true during the brooding phase, and also during the free-run phase, though only for the white-feathered birds. We also predicted that wing and wolf load bearing would increase with complexity, which we see a trend for during the brooding phase, but not during the free-run phase with the exception of Aviary 2 birds. At this point, we can conclude that the aviary design can promote dynamic load bearing and wing and wolf load bearing, with stronger effects for white-feathered birds. Aviary complexity could have beneficial effects on skeletal traits of laying-hen pullets reared in more complex aviaries, and hopefully decrease bone fracture prevalence and improve laying-hen welfare in the long run. Since analyzing data presented today, we reared a fourth and last flock of pullets, which will further contribute to this dataset and hopefully give us a clearer picture of the laying hen development in the different aviaries. We also plan on bringing this dataset into context of physiological traits that were assessed by a master student of our lab, Erin Ross. I also assessed navigational skills of pullets in this study, as well as long-term effects on bone health throughout lay. Here is some background reading for those that are interested, as well as the source material for graphics used that were not my own. And with this, I would like to thank all our funding agencies, as well as the staff at the Arkel Research Station for making this project possible. Also, all the students and research assistants that helped me collect this data. I appreciate everyone who listened in to this today, and I'll happily answer any questions